The reason I want to do this one is it kind of leads us into what we're going to be talking about today. So the probability of winning a certain game is 0.5. If at least 70% of the games in a series of n games are won, the player wins a prize. So it's not enough that you just win once. You have to win 70% of the time in order to get a prize. If the possible choices for n are n is equal to 10, n is equal to 20, and n is equal to 100, which value of n should the player choose in order to maximize the probability of winning a prize? So you get to choose, basically, think about it this way. You're going to flip a coin, right? And you have to declare, I'm going to get heads. And you have to get heads 70% of the time. Would you want to flip it 10 times, 20 times, or 200 or 100 times to maximize your chance of winning?
Probably not 100.
Why not?
Because it will most likely be closer to 0.5.
Exactly. When you do it a lot, that's the rule of large numbers. When you do it a lot, your experimental probability will get closer and closer to the theoretical probability. So here you would want to do it 10 times. Because the more you do it, the more it's going to start looking like the actual. That makes sense? Okay, I just wanted to do that real quickly because that kind of goes to something we're going to talk about today. These have been sticking up in my folder for like, I don't know, a month. Well, thank you. It's like, hand these back to Andrew, and I just...
Halloween?
That's really gross.
Well, a month would just be the beginning of December.
Well, this one goes back to November 16th.
So,
Little time capsule.
longer than a month.
Pumpkin pin.
All right, so today we're going to do something. This starts section 5. I know we haven't had our section 4 test yet, but we have to go on, otherwise we'll never get finished with all of the content that we need to before the AP exam. So we're going to talk about the sampling distribution of a proportion. So let's say that a particular microchip manufacturer finds that 20% of the chips they make are defective. By the way, if they did that, they would go out of business. There's no way you can have that high a defective rate. But I picked that just because it made this problem easier to do. All right, so if we were to sample 10 chips, we would expect to find 2 of them were defective. But even in a random sample, it wouldn't be 2 every time, would it? Sometimes 1, sometimes 3, maybe as many as 4. Probably not 5, right? But it would vary from sample to sample, right? That makes sense? Okay. That's technically called sampling error. Your book, I think rightly, makes a case for saying it's sample variation. Okay, one sample varies from another one. It's not really that the sample is wrong. It's just that they're going to vary. I'm like, I think that's a good idea. All right. But we would expect that the long-term mean for these samples would be a 20% failure, right? If we did it enough times, we would think, all right, we're going to get close to 20% failure. So we use P. It's a lowercase p. Notice we've used capital P for probability, right? So a lowercase p to stand for the parameter of the model for proportions. And you're like, the parameter of the model for proportions. That seems like an awful lot. Remember that a parameter comes from a sample. Or a parameter comes from the entire population, right? parameter, population. Statistic comes from the sample. Okay, you just remember the P's go together and the S's go together. So in our model, P is going to be the probability of success. In this case, it's 0.2, which is the proportion of defective chips. Okay, so let's suppose we were to look at all possible samples of size 1. You're like, why would you take a sample of size 1? Trust me, okay? It gets better in just a minute. I know it's ridiculous to do that. Fully understand. All right, and let's say that we had 1,000 chips in a day. And we looked at all the possible samples of size 1. It would look like this. 800 of our samples would have no chips defective, right? And 200 of them would have 1 chip defective. Correct? Okay, and you're like, that's a ridiculous looking distribution. Okay, the observed proportions, P hat, so the P with the little over it, that's P hat. That's the observed proportion. Sound effects are optional. So, and this is, I apologize, this is a badly worded sentence. It looks like it's saying 800 multiplied times P hat. It is 800 of the samples, P hat was 0. So if you want to change that somehow, I read it and went, 800 times P hat is 0. That doesn't make any sense. So of the 1,000 samples, 800 of them would have a P hat of 0, and the other hat would have a P hat of 1. Remember, P is the proportion, and the proportion has to be between 0 and 1. Okay? Now, note if we were to average this, well, we would do 800 times 0 plus 200 times 1 divided by 1,000. It comes out to be 20% or 0.2, which is exactly what we thought. Okay? So your book does kind of the same thing, but they do a random selection, and I'm like, I don't like it. So here's what I did. I spent a long time doing this because I had to figure out how to make the numbers work out. So what if we did a sample of size 2? If you did that, it turns out that you would have 640 of them where you wouldn't have any defective chips. You would have 320 where 1 was defective and 1 was not. And you would only have 40 where both of them were defective. You know, like, that's still not a very nice looking distribution, is it? But look what happens. If we do a sample of size 3, you're like, okay, well, that's still pretty skewed to one side, right? By the way, which way is this skewed? Yeah, this is right skewed. Wherever the tail is the direction that it's skewed. Again, I have had trouble with that. I always want to say it's skewed to where the big things are, but it's the other way around. But look what happens once we get to a sample size of 5. So we're taking 5 chips at a time. It's still skewed, but is it as bad? No. Okay, and notice here, once you have taken a sample size of 5, it's almost impossible to get 5 defective chips. Okay, it's a pretty small proportion. All right, look at page 2. So here is a sample, here is all the possibilities of a sample size of 10. This is starting to look more like something that we're used to. And I skipped over because I couldn't stand to do it that many times. Once we get to a sample of size 50. What does this look like?
Normal
It looks like a normal distribution. If we get a big enough sample, our sample proportion is going to start looking like a normal distribution. Looks like a normal distribution, or at least pretty close to it. So once your sample size is large enough with these proportions, we get something that looks like a normal distribution, and then we know all kinds of things about it. So this is called a sampling distribution model. So a sampling distribution model shows how a statistic, remember a statistic is for samples, in this case the proportion of defective chips, varies from sample to sample. So you're going to have an awful lot of them where, what is this number down here at the bottom? Underneath the biggest bar.
0.2.
Oh, 0.2. Isn't that our actual?
Sure is.
Wow.
There are more of those than anything else. And it's fairly normal looking. It's fairly symmetric. It's unimodal. You're like, okay. So we have already shown that the mean of the proportion of the sampling distribution is the mean of the population. Notice, go back. What's the highest bar on this one?
0.2.
0.2. Go back to the previous one before that. The biggest one was 0.2. As soon as we got anything that had 0.2, it was the biggest bar. Okay? So for any sample size, as long as you get over a couple, the observed p hat is going to be equal to the actual, which is p. So the mean of p hat is going to be equal to p. All those observations, if we average them together, so remember, this means the average of all observed proportions is going to be equal to the actual proportion. All right, what about the standard deviation? Well, remember that for a binomial model, the standard deviation of the number of successes for n trials was the square root of npq. You guys remember that, right? We just have done it. So since the sample proportion p hat is the number of successes divided by the number of trials, then the standard deviation of p hat, which can be written either of these ways, sigma of p hat, or a lot of times it's written standard deviation of p hat, is the square root of npq over n, or more simply, and we'll almost always do this, the square root of p times q over n. So now we've got the two things we need. We need the mean, we need the standard deviation. Once we have that, we can use all kinds of stuff. So when we draw random samples of n individuals, the proportions will vary from sample to sample. That's called sampling error or sampling variability. As long as n is reasonably large, and we'll talk more about how big it has to be in just a second, we can model the distributions of these sample proportions with a probability model that is the normal model where the mean is p and the standard deviation is the square root of pq over n. Okay? It's not terrible. And these are ones where I need to print off the AP formula sheets. It's on there. Okay? we need to start looking at those more often and saying, okay, this is where it is on the sheet, so you can get more used to looking those up if you need them. All right, so going back to the shoddy chip manufacturer, when our samples are of size 50, and that was the first place where it really started looking normal, the distribution model is the normal, where the mean is 0.2, and the standard deviation would be the square root of 0.2 times 0.8 over 50. Having done this chapter and the 4 subsequent chapters of homework, I've typed this thing in so many times it's not funny, because it comes up on practically every problem. And that comes out to be 0.2 with a standard deviation of 0.0566. How many decimal places you use on this? There is no set standard. I usually, look for a place where it's natural to cut it off, or 3 decimal places, whichever strikes my fancy on that particular day. Okay, that's part of why this is different than the AP Calculus exam, where there is a correct answer. Frequently here, there's like, there's some squishy room. Okay. So, what are our assumptions and conditions in order to be able to use this normal model? You're going to have to be able to state this. Okay. So, before you use a test, you have to state why you can use this test. So, when can we do this? First of all, the experiments. If it's an experiment, this means it was a random assignment of treatment. For surveys, it's got to be a simple random survey. Okay, most of the time, actually there's some of both, but a lot of times it's for surveys of some kind. Independence. The independence assumption is a tricky one. Most of the time, we don't really know whether those are independent responses or not. But we can look at how they got the data to see, is that assumption plausible? A lot of times we'll assume that this is independent. And as we saw in the last chapter, if we sample too much of the population, the individuals may no longer be independent. Therefore, we use the 10% condition, that the sample is less than 10% of the entire population. Your book, when you do the readings for this, it goes on and says, if it's more than 10%, there's a different formula, and we're not going to learn that formula. Okay, and at which point you go, thank you, I don't want to learn another formula. Well, no, to them, not to me. Okay? All right, so then there's the last one, the sample size assumption. The sample has got to be big enough. How big does it have to be?
Huge.
Enough.
There is no particular size, but what there is what's called the success-failure condition. That n, which is how big your sample size is, times p, the probability of success, has to be greater than or equal to 10. And the same for the number of failures. N, the number in your sample, times q, the probability of failure, must also be greater than 10, or greater than or equal to 10. It can actually be equal. At College Board, instead of saying n times q, they say n times 1 minus p. But we all know that q and p are complements of one another, so they have to add up to 1. All right, let's do an example. So, in a high school with 2,000 students, 30% of the students have a driver's license. Okay, so again, that's about the population. Suppose we select a random sample of 50 students and determine whether or not each has a driver's license and calculate the proportion of students that have a driver's license. What is the probability that more than 40% of the students claim to have a driver's license? So that's in your sample. Be sure to check the conditions and assumptions necessary. Okay. So, what was the first assumption or condition? You can look back a page.
Random assignment of treatments.
Well, this is not an experiment, so that doesn't matter.
And they have to be independent.
No,
Or no?
between the two.
The randomization condition.
Yes. He talked about random assignment of treatments. That's only for experiments.
Oh, simple random.
Simple random.
Yeah.
SRS.
Yeah, this is an SRS.
ERS. Sorry.
And 50 is less than 10% of the population of 2,000. Most of the time when you're doing these problems, you don't know the true population. Sometimes you do, sometimes you don't. In most cases, you say things like, 463 men is smaller than 10% of the world's population of men. Okay? Who'd have thunk it? Yeah. All right. So we've got the independence part. We've got the randomization part. What's the other part that we have to have?
Sample size.
Yeah, the sample size. So the expected number of successes in P is 50 times 0.3, which is 15, and the expected number of failures, you can either calculate it or you can just subtract the expected number of successes from the total, is NQ, which is equal to 50 times 0.7, which is 35, are both greater than the required minimum of 10. By the time this unit is over, you are going to be sick to death of writing that.
Right.
Just telling you. And I was talking to a couple of my calculus students who took stat last year, and they're like, yeah, it just gets super long. So, and I'm working all the problems, and I'm like, there's no way I'm assigning all the problems out of these chapters because it's just crazy long. All right, so we've met all the qualifications. All right, so what else do we know? Well, we want to do a normal model. And we want there to be, well, we expect that there's going to be 30%, right? So 0.3. And we know that our standard deviation is going to be 0.3 times 0.7 divided by 50. So that's a normal model where this is 0.3. Do I have these notes all filled out? An excellent question. If I do, they're probably back at my desk. So, E, did you already punch that up?
0.0648.
0.0648. Okay, so there are two different things that we could do here to figure out the probability that we're going to have more than 40%. Okay, we could do a z-score, or we could just go ahead and do a normal CDF. It doesn't really matter. Later on, we're going to do a lot where we do z-scores because that's the way they usually do it on the AP exam. But to save time for right now, I'm just going to do a normal CDF. I'm going to draw my normal curve. This is 0.3. We want to know the probability that more than 40%. So we want this right tail over here. Since I'm not doing a z-score, I have to tell them that I'm doing the normal CDF. If you're doing a z-score, you don't have to tell them that you're doing a normal CDF. That's the one plus to doing a z-score. So I'm going to do a normal CDF. When I do a normal CDF, the first thing I have to put in is the lower limit, which is 0.4, the upper limit, which is infinity. Got to put in the mean, which is 0.3, and the standard deviation, which is 0.0648. Remember that if you do this on the AP exam, you've got to label those things. So this is x, this is mu, and this is sigma. My sigmas always look awful. Notice how small your standard deviation is here. Does it seem real likely we're going to get up to 0.4?
No.
So let's see, two standard deviations would be 0.1. So what does that come out to be?
0.06139.
6319. So about 6.3% chance. All right. So, second question for this. If only 150 students sampled have a driver's license, should we be surprised? And you're like, what the heck? 150? My sample was 50. This is one where I go back to my desk because I know I have this back here. I changed some other number. 150 is certainly wrong. Yeah, how about 5? I found a couple of these that I typed up on the same day or a day or two apart, and they're numbers that make no sense at all. That's what I get for working on this over Christmas. All right, so if only 5 students, so 5 out of 50, well, that's 10%, right? So 0.1.
I think we should be surprised.
You think you would be surprised?
Yeah.
I think probably so. So again, I'm going to do a normal CDF. And I want to have, I'm going to do normal PDF, sorry. We don't do PDFs very often, do we? So let's look at that. I'm going to pull mine up. So if we do second vars, normal PDF, the X value is 0.1. The mean was 0.3 and the standard deviation was 0.0648. So before I hit enter, I'm going to write all that. 0.1 is X. My mean is 0.3 and my standard deviation is 0.0648. What's the probability? Not super low. 0.0526. So about a 5.26% chance. I think we discussed this earlier, but a lot of times we use 0.05 as kind of a cutoff. So this would be close to that cutoff, but not quite. All right, I think that's a good place to stop. We'll do sampling distribution of a mean on Thursday.
Can I go to bed?
You can. Just going to remind you, do you have a quiz on Thursday?
Yes, sir. Chapter 15.
Chapter 15? And the quiz on chapter 16 is next week.